We are now switching from crystalline silicon PV technology to wafer technology, and Stefan Reber will present a very innovative way to make crystalline silicon wafers. Mr. Reber, the board is yours.
Thank you very much, Eike. So thank you very much for the opportunity to present our NexWafe disruptive technology for producing of high performance, ultralight, low carbon footprint silicon wafers to you. So we have seen this graph already several times in this conference. It's not anyway very important to keep in mind. We are at the verge of a transition, a tipping point where we have to transit from carbon-based electricity and carbon-based power generation to renewable energy, which will take a high share of the energy market in the future. And the big question is photovoltaics, solar energy, solar electricity able to provide these thousands and thousands of gigawatts we need for this terawatt age? The answer is yes, as I will show you in the next slides, provided we will be able to implement more resource efficient and energy efficient technology for solar cells and modules in the future. So Gunther just had a good talk, and Gunther, thank you for this, showing that there are solar cell technologies available which can go to very high efficiency. So where's the issue? Where's the status and where's the issue? The issue is with the wafer. The wafer is produced currently in this manufacturing chain. It's starting with a silicon containing gas, the so-called chlorosilane. It's going over several process steps, which are either highly energy consuming, like polysilicon production, or ingot pulling, which works at 1,500 degrees roughly, or process steps which create a lot of waste, like cropping, bricking, and sewing, to produce finally a wafer which is not perfectly square. Usually it is pseudo square. What happens here is, from 1 ton of silicon contained in this polysilicon, which was produced with a large energy consumption, you only can produce a bit more than half a ton of wafers. The rest, that's all waste, 450 kilograms of waste, which is useless. So this process step, that's the one weakness, is energy intensive, and it emits lots of CO2 during this process. Second problem, this wafer has limitations in quality. There are champion wafers which are perfect and can achieve very high efficiencies, but the average is limited in performance due to the growth process. And third, thickness of these wafers is, or let's say more, the thinness of these wafers is limited. You can do wafers in mass production which are 120 micron or thinner. And that's what NexWafe tackles. We radically simplify the wafer production and produce a high-performant wafer. How do we do it? We start with the same raw material. It's good, it's cheap, and it's of very high quality. We end with the wafer, our Epinex wafer, full square wafer. But in between, we skip all those process steps which consume large amounts of energy or produce large amounts of waste. In the end, this means from 1 ton of silicon now, which is contained in the chlorosilane, we produce nearly 1 ton of wafers, 950 kilograms of wafers, nearly eliminating any waste stream in this process. And this technology allows us to consume or to produce wafers with 70% less energy, emitting 70% less CO2. In addition, we can control the properties of each single wafer to make it a champion wafer. So we have all high-performant wafers in average. And third thing, we do not have any constraints in reducing thickness and harvesting those nice additional benefits Gunther just mentioned. We can easily produce 50 micron wafers. So how does cell processing benefit from these wafers? We enable cell manufacturers, that's very simple, to produce 26% efficient cells in average, not champion cells. All and any single cell will have this efficiency. In other words, we are not producing, as for example P-type mono is doing that, cells with 6.4 watts per wafer, but our wafer will have 7.2 watts. Doesn't sound much, but if you do the math and the additional benefit on the module, that's tremendous. And we did this calculation over here. We calculated the added value per wafer for different technologies. And the benchmark is what we currently see in the mass production, the so-called P-type monocrystalline wafer, which according to IGRPV will be sold or will be cost around $23 per wafer in some years. And if you compare that with our NexWafer, the additional efficiency sums up to 18 cents added value, which you can attribute to the wafer, benefiting to us and our customers. And this is amazing. It's nearly the wafer cost of a P-type mono wafer. In other words, this turns down to drastically reduced levelized cost of electricity, and this then drives and enables the terawatt age for photovoltaics. But there are further interesting fields of application which are not minor important. One is decarbonization of transport. Electromobility is also in transition currently from combustion engines to electric cars. And these cars need photovoltaics to be integrated on their roofs in order to extend their range. And car roofs are not flat, they are bent. You need photovoltaics, solar cells, which follow this curved shape. And we can do that. Normal thickness wafer would break. We can produce thinner wafer, and you see it here in this picture above. Those thin wafers are like paper. You can bend them with a very minimum radius. So we can integrate highly efficient solar cells in any shape on a car, and by this make an important contribution to electrification of the transport sector. Another sector is communication and education. And you need internet to reach all regions of the world, all those rural, including those rural areas where there are no cables. And SpaceX and Amazon, they are announcing that they will build a satellite-based internet of the future with thousands and 10,000s of satellites. Each of them needs power, solar power. It's impossible to provide this solar power with the current technology. It's far too expensive. But we can provide this energy by using lightweight, thin wafers to power up these satellites at reasonable cost. And by this, again, enabling another sector, communication and education over the world. So what is our roadmap? We start soon with providing and producing 120 micron so-called drop-in wafers, which are enabling a 24-cell efficiency in average. Soon after that, we will have made the work to produce 80, 70 to 90 micron solar Epinex wafers in order to produce even higher efficiencies in average. This feed into these new nice thin cell technologies like heterojunction or others. At the same time, and we will hear a talk of that by Chris in a minute, we enable tandem solar cells based on perovskites, which can have even higher efficiency, 30% efficiency. We will hear that by Chris. We will in parallel work and enable this market for flexible, lightweight solar cells, for space solar cells by producing these 50 micron thin wafers. And it's important to keep in mind, we can do 26% cell efficiency for flexible solar cells. Usually it's half or even less. And the ultimate goal, which we also will access, is tandem solar cells based on gallium arsenide. Our core competence is providing technology which is able to produce high quality semiconductor layers gallium arsenide is a high quality semiconductor layers. We can do that with our technology, and by this enable ultra high efficiencies in square kilometer area, and by this enable the transition which we need in the world. With this, I thank you very much for your attendance. Open for any questions later on.